We're going to do some proofs, and when you do proofs in geometry, we got to use our toolbox. So I got all these things listed for your toolbox. If you have a sheet of paper with these on them, if you would copy this down on number 1, number 2, 3, 4, 5, and 10. You can push pause. I'm going to just keep talking. Numbers 1 and 2, those are definition of congruent sides and angles. They are the same thing. Um, Sometimes you're dealing with proofs that deal with sides of triangles. Sometimes you're dealing with proofs that are just segments, in which case you would use the correct one. So if you're dealing with sides of a triangle or square or something like that, you're going to use definition of congruent sides. If you're dealing with just segments, you'll use definition of congruent segments. What to notice about number 1 and 2? You've never done a proof before, that's okay. I mean, what's different on number 1 to number 2? Or, I mean, from just like this part to this part? Well, there's no squiggly line right there. This one means congruent. This one right there, that means congruent. So segment AB is congruent to segment CD. Over here, we're just talking about their measures being equal. So we're looking for that in a proof when we write definition of congruent segments or sides. Similarly, on number 3, we got definition of congruent angles. So notice again, the angles are congruent, and then their measures are equal. So we've got the measure here too. And it could go either direction. It could go that way or that way. Number 4, midpoints. Definition of midpoint on your toolbox. Midpoints make 2 congruent halves. It cuts line segments in half. Number 5 is a bisector. Definition of bisector. Bisectors can cut segments or angles in half. So bisectors will be a line that cuts things in half. Midpoints are just little dots, little points that will cut line segments in half. Number 10, blank is a right angle. This is definition of perpendicular lines. Perpendicular lines make 4 right angles. Whenever I see angle ABC is a right angle or angle XYZ is a right angle, the reason that it is a right angle is because there are perpendicular lines there. So in my proof, on my reasoning, I'm going to write definition of perpendicular lines. Next, on number 14, this is segment addition postulate, adding 2 smaller segments to get a larger segment. So I wrote AB plus BC equals AC. I got AB plus BC equals AC. 2 smaller segments added together to give me a larger segment. We'll see that here in a little bit. Number 15, adding 2 smaller angles to get a larger angle. So just like on number 14, it was segment addition postulate. This one's going to be angle addition postulate. So I've got angle AMX, that's that angle right there, plus angle XMB, that's that angle right there, will equal angle AMB. So that's the big angle. So the 2 smaller angles added together give me the larger angle. Number 20, AB is equal to AB. Whenever something is congruent to itself or equal to itself, it is the reflexive property. I always think about a mirror and reflection. That is the reflexive property. It's not the reflective property, but it is the reflexive property. Number 22, if A equals B and B equals C, then A equals C. So I always think about being able to write 1, 2, 3 things equal to each other. And if you can mark out the middle like that, you'd have A equals C. So I just think about if I can write it with 3 things equal to each other, mark out the middle, that's called the transitive property. I could also do this. I wrote some inequalities over here on the right side. If A is less than B and B is less than C, then that means that A is less than C as well. Okay, it could work with the same way with those. Number 23, every right angle is congruent to every other right angle. That seems really obvious. At some point, we're going to have to prove that it'll say this angle is congruent to this angle. And you'll say, why are these angles congruent? Like it hasn't said anything else in the proof. Well, they're both right angles. So right angle congruence theorem tells us that they are congruent. A little bit later on in our proofs discussion, we'll talk about these things down here when we talk about triangles being congruent, and we'll use this as well, but make sure you copy those down on your toolbox. So let's slide down to right here. So I've got a proof. Whenever I'm giving you a proof, I'm going to have a given. I'm going to have a picture. You don't have to circle this. And I'm going to have what you're going to prove. There will be a column of statements. There will be a column for reasons. Most of the time, I don't want to say most of the time. To start with, we're going to fill in all the reasons. Where are we going to get all those reasons? From our toolbox. Okay. So I'm going to give you all these statements to start with. You're going to have to fill in all the reasons with your toolbox and go from there. All right, let's delete that. So first, 99% of the time, first one is going to be given to you. So I have BC is congruent to DE. I'm looking at step number 1 right here. BC is congruent to DE, and I can find that right here. It's given. And 99% of the time, that given is going to be right there. Okay. Reason number 2. What I'm noticing is that this looks awfully similar to this. What's different about it? Well, we got this little squiggly line right here that's, on number 1, but not on number 2. That squiggly line above the equal sign means congruent. So I've got the segments BC and DE are congruent in number 1, and number 2 is telling me that their measures are equal. Okay. And when I do that, I'm looking on my toolbox at number 1 or number 2, and I'm trying to decide, well, is it definition of congruent segments or is it definition of congruent sides? I know that it's segments because there are no sides here. There are no triangles or squares or anything like that. So this would be definition of congruent segments. Number 3, okay, I've got AC is equal to AB plus BC. AC, this whole line segment up here, is equal to AB, this part, plus BC, this part. So I have 2 smaller segments added together to give me a larger segment. That would be segment addition postulate. Okay, 2 smaller segments added together to give me a larger segment. Segment addition postulate. Number 4, there's good guesses and bad guesses when it comes to proofs. For example, a bad guess on number 4 would be definition of congruent angles. Why is that a bad guess? Well, there's no angle symbol anywhere. There's no angles up in the picture. That's a bad guess. Something that would be a good wrong guess would be segment addition postulate. You got 2 segments right here, A, B, and DE. You're going to add them together. They'll give you a longer segment. That's an okay wrong answer. It's still wrong, though. So what's different from 3 to 4? Well, I'm noticing that BC has now become DE. Why can I write that? Well, up here, we said that BC is equal to DE. So I can substitute that in. Substitution is going to be our reason. Substitution. Pen is not cooperating. Substitution. And we're done. Proof number 1, done. Let's look at another one. Given A, B, and C are collinear, what does that mean? Well, they're on the same line. Look at A, B, and C right there. They're all on the same line. AB is equal to BD. And BD is equal to BC. Okay? And we want to prove that B is the midpoint of AC. So all that first stuff, that's given. The next one says AB is equal to BC. Well, where did they get that crap from? I don't know. I do know. Spoiler alert. I could write this. I'm going to take this information. AB is equal to BD. That was the first one. But I also know from the second one that BD is equal to BC. I can mark out that middle one, and then I'm left with AB is equal to BC. We talked about something earlier where you can mark out the middle. That's the transitive property. Transitive property. Okay. Going from number 2 to number 3, I'm noticing that, you know, not to oversimplify it, but I've got a squiggly line now. I've got a congruent symbol. The letters are the same, the segments are the same. I'm just kind of restating it in a different way. Definition of congruent segments is what we're looking for here. Definition of congruent segments. Right? There are no sides up there. There's no side to a triangle or square, so these are going to be segments. And lastly, B is the midpoint of AC. I don't really like this answer, but we're going to call it a definition of midpoint. We'll show you here in a second when the most correct time to use definition of midpoint is, but just kind of accept that and then we'll move on. Next, I got B is the midpoint of AC. B is the midpoint of AC. Okay, so I'm trying to prove that AB plus CD is equal to BD. First part's given. And all right, if B is the midpoint of AC, so I've got AC is all of that right there. And if B is the midpoint, that means it's going to cut that in half, right? So that means that AC is getting cut in half. That means that that is congruent to that. So if B is the midpoint, it's the point that's cutting that thing in half. AB is going to be half, and BC is going to be the other half. So why is AB congruent to BC? Because B is the midpoint. By definition of midpoint. And this is when you will see definition of midpoint. I'm going to tell you something is the midpoint. And then at some point in the proof, I'm going to say, here are your two congruent halves, just like we did in our toolbox. And when you get those two congruent halves, why are they congruent? Well, definition of midpoint. Number 3, BD is equal to BC plus CD. BD, this whole line segment, is equal to BC plus CD. We got two smaller segments added together to give me this larger one. That's segment addition postulate. Lastly, if I'm looking at steps 3 to 4, what's different about steps 3 to 4? So I'm noticing that BC and AB have swapped. So everything else is the same. The BD and the CD are exactly the same. I've just substituted those. Why can I substitute those? Well, AB is congruent to BC. So I can substitute that in. So let's say substitution. Okay. Next proof. B is between A and D. C is between A and D. Given. Okay. B is between A and D. C is between A and D. AB plus BD. AB, so this small segment plus this small segment is equal to AD. Pin's not working. Segment addition postulate. Segment addition postulate. Okay. Next, we've got AC plus CD equals AD. Same thing, segment addition postulate, right? Yes, you can have the same thing twice. Segment addition postulate. Number 4. So let's write this first. I'm going to go back to this proof right here, and I want us to look at this. Okay, remember how I could write that? There was a BD in both of those equations. So when I look down here, and I'm wondering how they got that's equal to that, well, both of those things that I just underlined are equal to AD. So I could write something that looks like this. I'm going to write it up here under proof. AB plus BD is equal to AD. Okay, so I got that from that one. And then I know AD is equal to AC plus CD. Then I can just mark out the middle, and now I have what number 4 is. That's transitive property. Okay. Let's slide down a little bit. Yeah, we can do this one. Try this one. Pause the video, see if you can do this one. M is the midpoint of AB. B is the midpoint of MD. That's given up there. So if M is the midpoint, of AB, that means that that is congruent to that, correct? So I'm going to look in my proof, and when I see AM is congruent to MB, I know that those are congruent because of definition of midpoint. Okay, how convenient. AM is congruent to MB. Definition of midpoint. Okay. And likewise, it says the same thing for MB and BD because B is the midpoint. Okay. MB and BD are congruent. Definition of midpoint. From numbers 2 to number 3, what am I noticing? Well, I'm noticing that these congruent symbols are changing to equal signs, and the lines above them, the segments are going away. So now I'm only trying to decide, is it definition of congruent sides or definition of congruent segments? Well, there's no sides to anything, so this is definition of congruent segments. Okay. Next, number 4, MD equals MB plus BD. So we have this segment right here. MD is equal to MB plus BD. Segment addition postulate. Two smaller segments added together to give me a larger segment. Number 5, when I'm looking, the only thing different is BD changes to MB, right? How can I do that? Well, MB is equal to BD. So all I did was substitute it in. Substitution. And lastly, it's not necessarily on your toolbox. You could just say addition if you wanted to. We said MB plus MB is equal to 2MB. You could also say simplify. That would be fine. I'm going to say addition, though. Simplify would be fine, too. Okay. Let's see if we want to do another one. Yeah, that one looks good. See if you can do 1 through 3 right here. Push pause, see if you can do 1 through 3. Number 1 is given to me. And when I look at the difference between number 1 and number 2, the only difference is that congruent symbol again. Measure is showing up now. If I look at my toolbox, definition of congruent angles. Definition of congruent angles. Number 3, I've got EDG. EDG's up here. EDG is equal to the measure of angle 1 plus the measure of angle 2. So I have two smaller angles right here adding together to give me a larger angle. That is angle addition postulate. Angle addition postulate. Okay. And this next one, I could argue that it's a really big transitive property where you're going to mark out the middle stuff. But we're going to say substitution here. Substitution. And what we did was we took, let's back up. I know that 1 plus 2 is equal to EDG. So I got this 1 plus 2 right there. I also know that 2 plus 3 is equal to FDH. There it is right there. So all I did was substitute and plug in. Okay, next question is, how did I get from 4 to 5? Well, there's something missing, and that's the measure of angle 2 on both sides. So what I did was, it's just like an algebra problem. I subtracted the measure of angle 2 from both sides. So over here, it's one of those you could have written simplify, but let's write subtraction. I don't want to do this whole proof, but let's just look at the first two. The first one's obviously given. AB is perpendicular to BC, and 2 is congruent to 3. This upside down T thing is perpendicular, so that's important. Number 2 is the one that I really just want to talk about. ABC is a right angle. Well, how do you know it's a right angle? Well, we just said that AB is perpendicular to BC. If you look at your toolbox, then number 10, blank is a right angle. Angle ABC is a right angle. I think on your toolbox I put quotation marks around it. So this is definition of perpendicular lines. How do you know it's a right angle? Because there are perpendicular lines there. Okay, that's all I want to do on that proof. If you would, try this one and push pause, try it, and I'll give you the answers here in a second. Angle AEC is congruent to angle DEB, that's given. Angle AEC is congruent to AEB. All right, hold on. AEC is congruent to AEB, that's that one, plus BEC. That's two smaller angles. Added together, give me a larger angle. Angle addition postulate. Okay. Now I've got DEB. DEB is congruent to BEC plus DEC. Same thing again, right? Angle addition postulate. Next one. It's just like that other one where we did substitution, and it looks a lot like this one. It's this step right here, okay, where we took the 1 plus 2 right there, we took the 2 plus 3 right there, we plugged it back in up there. So what we're doing is, I know that AEC is equal to AEB, so I'm substituting it in right there. And I know that DEB is equal to BEC, and I'm plugging it in right there. So number 4 is substitution. Okay. And then to number 5, what's missing from 4 to 5? Angle BEC. So just like on the previous one, I subtracted it. Subtraction.